objective optimization. Okay, you're recording. And completely positive relaxations. And no worries if you're not familiar with any of the two topics. I'm going to give a quick introduction to multi-objective optimization and also to these completely positive relaxations. They have become very famous a few years ago because what you can do with these relaxations, this goes back to a very famous paper from Samuel Burra. What you can do is you take non-convex problems, non-convex quadratic objective functions, for instance, or mixed binary problems, and you reformulate these problems as very nice linear problems. So the miracle comes from the fact, so you start with a difficult problem, a hard problem, and then you end up with a linear problem. And the miracle is that the linear problem is a linear problem over the cone of completely positive matrices. So all the difficulty from your original problem is moved to checking whether a matrix is an element of this difficult cone or not. And because working with cones, continuous convex problems with cones is something much more, a big group of people is familiar with, continuous people. And by studying these completely positive problems, this allows you to handle, for instance, combinatorial optimization problems a continuous person would not have touched before. And it gives the hope that based on studying these completely positive relaxations that you can deliver, for instance, bounds for these hard problems coming from combinatorial optimization similar. And for that reason, a lot of effort was spent for a while in studying these problems and these relaxations. And I'm going to tell you about those relaxations, and then I'm going to study whether we can apply the same techniques to multi-objective optimization problems. Of course, clearly the hope is that when it is a powerful tool in single objective optimization, it will also be a good, powerful tool in multi-objective optimization. But I can already spoil the result now. It's a negative result, so we can apply it. We get some solutions, but all we get, and we can even prove that, are the somehow boring solutions. Solutions we would get with a much simpler tool anyway. And for that reason, it makes no sense to make the same techniques in the multi-objective setting, which is somehow clear if you have been working in both fields, but was never studied before for me really clarifying what you get and what not. So let me start with a single objective setting to explain to you what are these relaxations based on the cone of completely positive matrices. So it works, at least in the most famous paper by Samuel Burra, for this class of problems here. So you have quadratic objective functions, which might be non-convex. So the non-convexity, the difficulty of your problem can come from these non-convex quadratic objective functions. Then you have nice linear constraints, non-negativity conditions, and this is a subset of the indices of your variables. So some of your variables might take binary values only. So the non-negativity, the non-convexity can also come from these binary conditions. And the miracle will be that you reformulate those as simple linear problems over a specific cone. For doing so, you need that a specific key assumption is satisfied. This is what Burra wrote in his paper on the first or second slide, and we will also need these assumptions throughout the paper. It's more or less a very weak assumption because if you do not have it, you can easily guarantee it. So what you need is that just based on your equality constraints and the non-negativity, you already guarantee that those variables for which you require that they take binary values only, that they are already in the interval between 0 and 1. And in case you do not have satisfied this in your original problem, you just need to add additional inequalities. Then you have to transform those to equality constraints. So you will need a few more variables, but then you can easily ensure that this assumption is satisfied. Just to let you know, we need this in the beginning, and to reformulate it might add additional variables. That's all. So you take this problem here, and for the reformulation, we will need the cone of completely positive matrices, which is defined here. So you take some matrices, symmetric matrices of order n, and it is called completely positive if it can be written in such a form here. So a sum over rank 1 matrices. It's in the convex hull of rank 1 matrices. You can also define it in such a way. You can also ask what the smallest number are, such that you can write it as such a sum. So for instance, rank 1 matrices are completely positive matrices, as long as the vector for which you build a rank 1 matrix is non-negative, but you can also generate further matrices by taking sums of such rank 1 matrices. And the smallest number R for which you can represent your matrix X in such a way has also a specific name. It's called CP rank. We will not need it on the further slides. It's already a lot of work to find the CP rank for a specific matrix if possible at all. And if you now take the union of all those matrices, you will see that it's a cone, and it's called the cone of completely positive matrices. It has a lot of nice properties. It's a closed cone, pointed, convex cone, so it defines a partial ordering in your space of symmetric matrices. And as long as you're in small dimensions, you can handle it very easily, because these are those symmetric matrices which are component-wise non-negative and positive semi-definite. So these two properties describe exactly your cone of completely positive matrices as long as n is less or equal to 4. As soon as n is strictly larger than 4, you only have that this is a strict subset. And then working with this cone is in fact pretty hard. So it's already hard to check whether an arbitrary matrix is an element of this cone of completely positive matrices. But what you can do, for instance, so you have later on an optimization problem where this cone defines your feasible set, among others. You can go over, for instance, to this larger cone here, then you make your feasible set of your optimization problem larger, and then when you solve your problem, you get, of course, a lower bound. And there exists a lot of discussions, approaches for finding approximations of this cone, which are in a better way to handle numerically. It's like inner and outer approximations for finally working with them. But you will see that we start with a complicated problem, and the difficulty does not really go away, despite we end up with a linear problem, and the difficulty will be hidden in the fact that you have to check if some matrix is an element of this cone, yes or no. And now we come to the reformulation, and I will show you a few of the steps in between how we come to this relaxation, but first it will just be a reformulation. And what you have to do is, so this is your original problem, you just rewrite for a start the objective function. This here is a scalar, and here we have written an inner product, which is the inner product, the standard inner product for the symmetric matrices, the trace. And the trace, the value of this expression here is nothing else than this real number. So at the moment, we really just did a reformulation. We just wrote it in a different way. No more changes. We still have here these remaining parts of the feasible set, which can also be reformulated, included. But before we do that, we copy this equality constraints and write them another time, and this time to the power of 2. So on the left-hand side, we did have a scalar. On the right-hand side, we did have a scalar. And here we just make scalar to the power of 2, like you can see here on the right-hand side, it's a BI. We also do it on the left-hand side, and by using again this formulation of the trace of the inner product, it looks like that. We can at least write it like that. But still, it's just copying a redundant equality constraint. And as I've said, x less or equal to 0, we have to copy this. And now we have this condition that some of the variables should only be binary. And this can, of course, be expressed in such a form because the solution of this equation is only 0 or 1. And this is the first step. At the moment, it's a full reformulation. What we will do in the next step is whenever this matrix here appears, which is a rank 1 matrix, replace it by the name capital X. And as long as we keep this inside as additional constraint, it's just a replacement. And then, of course, if we do this, we can here replace xj to the power of 2 by the entry jj on the diagonal of this matrix X. And if we do this, so we rewrite everywhere where x transpose appears by a capital X here and there, and we keep this equality here, it would still be a full reformulation, no relaxation. The relaxation comes by the fact that in the next step, we ignore this equality here and we no longer write this additionally, and we allow for more general matrices here at this point. Not only rank 1 matrices with non-negative vectors, but with vectors from the convex hull of rank 1 matrices, which will be exactly the cone of completely positive matrices. And this is now the relaxation. So we did not do anything fancy here. This is still our objective function, just with, as you have seen it here, x transpose replaced by capital X. Still the linear equality constraints to the power of 2, and again x transpose, the rank 1 matrix replaced by capital X. This assures the binary variables. And this here is now new, and you will no longer find what's written here. So we replaced it, and now we relax it to that X is now just an element of this cone of completely positive matrices. Here you also have X appearing, which ensures to you that X is non-negative, but for the matrix you relax, you allow more matrices than just the rank 1 matrices. So for that reason, this is in fact a relaxation. It's a linear optimization problem over the cone of completely positive matrices. And the strong results are that you can show that despite you're considering a relaxation, this relaxation is tight in the sense that the optimal values are the same. You get from the optimal solutions of one of the problems, the optimal solutions of the other problems, and so on. So the results are the following. If one of the problems is solvable, then the other problem is solvable, and the optimal values coincide, are the same. Then if you have an optimal solution of the relaxed solution, then the X, the vector from this pair of the optimal solution of the relaxed problem, then the vector is at least in the convex hull of the optimal solutions of the regional problem. We will even get some further stronger results, which come now. So when you solve the relaxed problem, then you might have a lot of solutions, and in the set of optimal solutions, you will always find solutions which are of this form. So the matrix part here is in fact a rank 1 solution, a rank 1 matrix. And then if you take such a rank 1 optimal solution of your relaxed problem, so where the matrix is a rank 1 matrix, then the vector of this pair here is in fact an optimal solution of your original problem. So you get somehow, you derive from the solutions of your relaxed problem, in fact, the optimal solutions of your original quadratic problem. The optimal values are the same anywhere, you get the optimal solutions, and it's also working the other way around. When you have an optimal solution of your original quadratic problem, then you can immediately build an optimal solution of the relaxed problem. And these are the very strong relations between these two problems. So you can go over to a linear problem over the cone of completely positive matrices. Here is a corollary which collects all the results which are known about the relation of these two problems. So as I've said, when you have an optimal solution of your regional problem, you will know that you can find all these optimal solutions as part of an optimal solution of your relaxed problem. So there exists such a matrix X such that the pair here is optimal of your relaxed problem. When you solve your relaxed problem and consider only the first part of these pairs here, the vector X, this will be in the convex hull of all solutions of the quadratic problem. Then what's more important, when you just consider those solutions of the relaxed problem where you have here a rank 1 matrix, then this is exactly the set of solutions of your original problem, as long as you only study the first component and the values are the same. And now the next step will be to check if you can use all of that also in the multi-objective setting. So for that reason, I'm going now over to multi-objective optimization. I'm going to give to you a short introduction. I need several notions of optimality. They all will become important on the next slides. And I'm starting with a notion which is most famous, which is considered to be the optimality notion for multi-objective optimization. So what means multi-objective optimization at all? We have multiple objectives, for instance, n functions which we want to optimize at the same time. Typically, in general, we assume them to be competing, so we will not find a feasible point which minimizes all objective functions at the same time. And just to mention, there are different ways of comparing these vectors. So we can write all the objective functions in a vector, and for that reason, people also speak of vector optimization. There, in fact, exist different ways of defining optimality. So you can say, let's first introduce an arbitrary partial ordering in the image space and so on, but we will keep it simple in this talk. So we'll use the most basic concept, which says we are comparing vectors just component-wise. So for those being more familiar with the concept, this means we are just taking the natural ordering cone, the most simple cone, the component-wise natural ordering. So you can think as an example of you want to buy a new bike, and a bike should be as lightweighted as possible if you have to carry it for some parts of the path, and if you just lightweighted bikes are nicer to use. But of course, you do not want to spend too much money, so it should be cheap at the same time. Unluckily, the cheap bikes are typically the heavy ones, and the lightweighted bikes are the more expensive ones. So you would have two competing objective functions. And then you're asking for optimal solutions. And then you are saying an optimal solution is a feasible point such that there exists no other feasible solution, no other bike in your bike store, which satisfies all objective functions as good and is strictly better with respect to at least one of the objective functions. So for the bikes, this means you have an efficient bike if there is no other bike in the bike store which is as cheap and as lightweighted, but not cheaper or lighter. You can only improve one of the objective functions for the price of worsening one of the others. So there might be a bike which is much more lightweighted, but you would have to pay more for it. You get not a lighter bike without paying more. Then you would have an efficient bike. And of course, as you see with the bike example, a lot of bikes in the store might be efficient, might be optimal, non-comparable. So one might be an efficient bike, which is very costly, but very lightweighted, and another bike might be optimal, also called efficient, because it's very heavy, but at least very cheap. So if we illustrate this notion, here it's written in a set notation, and the illustrations we are doing typically in multi-objective optimization in the image space. So here is F1 and F2. You take a feasible point X, calculate F1 of X and F2 of X, then you get one of those points. And this might be, for instance, such an image set. Here, for instance, for a non-convex problem, and then the images of the efficient solutions, we are also calling them non-dominated solutions, can be found on the boundary, on the lower left boundary of your image set. For instance, this point here is an image of an efficient point because you cannot improve the function F1 without worsening F2 and the other way around. This point here in the middle of the set is not an image of an efficient point because you find another point which is strictly better with respect to both objective functions. So this is a standard notion. Typically, you're searching for efficient solutions. But on the next slide, I have to introduce the notion of weak efficiency, which is not so attractive from a practical perspective, but we need it very often in multi-objective optimization because KKT conditions, optimality conditions, scalarization results like a weighted sum approach, a lot of theoretical concepts only guarantee to us to find these weakly efficient solutions. And then after that, I'm explaining to you what is the supported solution because it will become very important on the next slides of the talk, because those are the points we are getting with these relaxations. But let me start with weakly efficient points. They are really a weaker optimality concept in the sense that any efficient point is weakly efficient. So more points are weakly efficient than those which are efficient. So now you're just looking for other feasible points such that all objective functions are strictly better. So you would still call a bike weakly efficient as long there is no other bike which is really strictly cheaper and strictly more lighter. But you would still call it weakly efficient if there's another bike for the same price which weighs much less. So from a practical perspective, you would not be interested. You do not want to go out of the store with a bike which is just weakly efficient and not efficient, because it would mean that you would still be able to reduce the price or the weight without necessarily spending more on the other objective function. Still, as I've told you, they are very important from a theoretical perspective. They appear all the time in multi-objective optimization. I'm going to show to you a picture on the next slide. Let me shortly already mention the supported solutions. A supported solution is what you're getting if you're just ignoring that you have a multi-objective problem and you just sum up your objective functions, simply said. So many people have a multi-objective optimization problem, in fact, but they don't know how to handle it, how to work with it, and then typically they just sum up all the objective functions. No matter if you sum up weight and price and whatever, very often they multiply these functions first with a weight. So this vector W here can be interpreted as a vector of weights. So you take those to be non-negative, and you can, without loss of generality, sum them up to 1. So they make a weighted sum of the objective functions, and you just minimize this weighted sum, and then you take the minimal solutions of this weighted sum. And any solution you're getting by doing so is called a supported solution. So we have to understand how they are related to our original multi-objective problem. A lot of people use this weighted sum approach. I call it weighted sum approach without knowing what they are doing, but it will become clearer on the next slide that it's not a good idea to make this approach in a non-convex setting. And recall these reformulations we are going to use are especially of interest for non-convex setting when we have a non-convex quadratic function or binary variables or whatever. So comes now an illustration of weak efficiency. At the left-hand side, you see the set notation. On the right-hand side, you can still see the illustration of the image set of efficient solutions. And now let's have a look here in this part and that part. I go over to the images of weakly efficient solutions, and you can see that we added some points here and there. I go shortly back and forward, so you can see that we added points. And for instance, this point here is an image of a weakly efficient solution, which is not an image of an efficient solution, because you can still improve the values for your function f1 without worsening the values of f2. Still, you would not like to have it in practice, but because let's assume f1 is the price and f2 is the weight of your bike, you could spend less for the same weight of a bike. These are the weakly efficient points. And now we are speaking more about the supported solutions. So first, you have the nice result that when you make this weighted sum approach and solve those problems, and define those points to be supported solutions, then they are guaranteed to be at least weakly efficient, which already sounds like a very nice property. The problem is the other way around. You also want to have that any weakly efficient solution is a supported solution, but this is only true in a convex setting. So only if you have some nice convexity, you have that any weakly efficient solution is a supported solution. And this means if you have not this nice property and you still just study supported solutions, make this weighted sum approach, you might not be able to find all weakly efficient solutions. And if you're not able to find all weakly efficient solutions, you might not be able to find all efficient solutions. So you might losing some points which are of interest. This is written here. So you might lose efficient solutions in case you're only concentrating yourself on the supported ones. So you need convexity, and this is, for instance, ensured in all the objective functions are convex and your feasible set is convex. We call for those problems of interest to us. We will not have these nice properties. Binary variables prevent us from having a convex feasible set, and quadratic non-convex functions are not convex functions, of course. And I try to illustrate this here, what's happening. So this illustration is now again in the image space. We have two objective functions, and assume we have just a full discrete problem. So our feasible set is a discrete set. So we have here just a finite number of points. Then it's very easy to find the non-dominated points, or the images of efficient points. For instance, this point here is an image of an efficient point, that point. And the orange dot is also an image of an efficient point, which might even be exactly the bike you want to buy in the end, because this is exactly the price weight combination you're most favorable with. And now what's happening with this finding supported solution where we minimize such a weighted sum of the objective functions. Minimizing a weighted sum corresponds to minimizing a linear function in the objective space, like it's illustrated here, and the weights tell you how the steepness of this line is. So when we vary the weights, we vary the steepness of this line. And then you easily see that we will only be able to find points which are on the boundary of the convex hull of the image set. So what I've now drawn is the convex boundary of the convex hull. And no matter how we vary the steepness of this line as an optimal solution, we will only get those non-dominated points which are on the boundary. We will never be able to retrieve this orange dot. So the orange dot is an image of efficient point which cannot be found as a supported solution, which cannot be found by a weighted sum solution. And this should illustrate to you that for non-convex problems, just taking supported solutions means you exclude points you will never be able to find, which might, from the application perspective, be exactly those points you would like to find in the end. And now we've learned about these supported solutions for multi-objective problems and more generally efficient points. And the final aim will be to find those from this specific multi-objective optimization problem. So now we have quadratic objective functions, like in the single objective setting. The objective functions might even be non-convex, so the quadratic Q's here do not have necessarily to be positive semi-definite. And the feasible set look like we have seen in the beginning for the results from Sambura. And the question is now, what comes out if you make the very same lifting steps as you've seen before and this relaxation in the space of matrices? We'll discuss that very soon, but to spoil you already now, to tell you that we are now having really a much more difficult problem than we did have in the single objective setting, I would like to add a small further excursus to some additional slides to point this out. Let's for a moment, very shortly, come back to the single objective setting and have a very specific setting. So we have here this one objective function for our problem. And let's assume this is even convex. So we have here a positive semi-definite matrix. And let's assume we have only one variable which takes binary values only. So we did have the subset B, which defined for us how many of the variables should take binary values only. And here it's only 1, 0, or 1. Then you would not call this a difficult problem, because what you typically would do is you fix x1 to 0, you fix x1 to 1, and then you have two very nice convex optimization problems. You solve each of these nice convex problems very quickly. You get two optimal values, you compare those, and the smaller value is your overall value of your original optimization problem. So it's not a hard problem. And now let's have a look at the situation, what's happening in the multi-objective setting. In the multi-objective setting, so we keep it as simple as possible. We just add one further objective function, and we still assume that also F2 is convex. Still nice linear constraints, and we fixed x1 to 0 and to 1 like we did on the slides before. And now what's happening is that we have two multi-objective convex optimization problems. Bi-objective optimization problems, but still that does not exist any method which delivers to you the full set of optimal values of these problems. It just not exists. We have ways of finding approximations, coverings, representations, whatever, but no method delivers to you the full set of optimal values. And even if you would be able to find the full set of optimal values, these are set of values, and in the end, you would have to compare these sets. Here, it has just been in the single objective setting, there have been values. These are scalars. The optimal value is a scalar. Here, the optimal value is a set in R2, and here also. It might look like I've drawn here on the slide with two different possible settings, what might happen. So let's assume you have fixed x1 to 0, and then you calculated the non-dominated set, so the set of images of efficient points. And this should be this green line here. And then you fix x1 to 1, calculate the images of efficient points. Some people call it Pareto curve or whatever, and this should be this line here. So we have two sets, and the overall optimal non-dominated set of the original problem would be this line here. So you did spend a lot of effort potentially to calculate these parts here, which do not contribute to the overall non-dominated solution set. On the right-hand side, it's even worse. All the points from the orange part here do not contribute to the overall non-dominated solution set at all. So you spend a lot of work. You can ignore it, skip it, waste the effort. On the other hand, this is a bit more closer to the single objective setting, because in the single objective setting, people say they're speaking of optimal integer assignment. So if someone tells you coming from heaven, what is the optimal integer assignment of your problem? So then you can fix these integers to this assignment, solve the problem, and you're done. Here it would mean if someone tells you x1 equal to 0 delivers to you the optimal solutions. Here on the left-hand side, all integer assignments contribute to the overall optimal solution set, which makes it even worse. So you might have a full list of optimal integer assignments. So it's much more difficult. Let's now come back to the approach what we have seen from Bura, and let's try to apply it to our quadratic optimization problems here. And we're doing the very same steps. So the feasible set after this lifting and relaxation looks exactly the same, of course. And we are repeating the steps for all the objective functions. So all are linear objective functions now. And again, the difficulty is moved to this cone of completely positive matrices. And of course, still, again, some kind of convexification did happen. This was overall the aim, to end up with a linear problem over some cone, which is a convex cone. So we end up with a convex problem. Also, this is a convex problem. And in the single objective case, this did not destroy anything, because somehow from your convexified problem, the optimal values have still be the extreme points of this convexified problem. And this is what's happening here, that we're losing something. So as a first note, which is completely clear, of course, this is a convex problem. The image set, so all possible attainable values form a convex set. And because we have a convex set, we have learned that the weakly efficient points are exactly the supported solutions. The supported solutions have been those points which we can find by a weighted sum. And they are always weakly efficient solutions, and the other way around, if and only if, did only work in a convex setting, and we have a convex setting here. So for the relaxed problems, weakly efficient solutions and supported solutions are the same. And this gives us already all the hints we need for the further studies that something will go here. So what is the supported solution of the relaxed problem? It just means you make a weighted sum of your objective functions, like we have seen on the other slides. And now we can check what we still have. So whenever we solve our relaxed problem with this completely positive cone and we find a weakly efficient solution, then we know there will also be a weakly efficient solution of the relaxed problem, which has your rank 1 matrix. So far, so nice. If we take a rank 1 solution of our relaxed problem, then X, this vector which belongs to it, is in fact a solution of our original quadratic optimization problem. But now the bad things start. We are immediately ending up with supported solution. So in fact, this already tells us that whenever we try to solve our relaxed problems and try to retrieve solutions of our original problems from that, we will only be able to end up with supported solutions. Supported solutions are those we did get by a weighted sum. So what we could have done from the very beginning, take our multi-objective problem, make a boring weighted sum approach. Boring because we should not do it in the non-convex case, and it's simple. Of course, we can make a weighted sum anyway, and then we use all the results from single objective optimization. So we are not finding anything new. We would only find what we get by a weighted sum anyway. The other way around is also true for all supported solutions of the regional problem. This here is the weakly efficient solution of the problem. So this already shows to you that all of this lifting, relaxation, now it's telling that my internet connection gets unstable, but you're still there. I see you blinking. Okay, hopefully it stays. So what I want to say, that we are missing points which are of interest, exactly those which are not found by a weighted sum. We can study this a little bit further, though first let me state that we do no longer have relations between the sets here on the left and right-hand side. We would like to have relations between the efficient points of the original problem and the efficient points of the relaxed problem, or at least for the values of the original problem, the values have been the non-dominated points and the non-dominated points of this completely positive reformulation. But in fact, we do not have this equality here like we did have in the single objective setting. We're losing this. The only thing what transfers, and which is somehow similar to what we learned in the single objective setting, is when we study all pairs of solutions of the lifted problem, the completely positive relaxed problem, and just take the vector x from these pairs, then they are in fact in the convex hull of the weakly efficient solutions of the regional problem. But also here, there is a but. It's written again here. At the moment, it's but a copy of the result we've just seen, just to have it on the upper part of the slides. We can tighten this result, improve this result. We can improve something more. We can prove that this set here on the right-hand side is not just in the convex hull of the weakly efficient solution. It's in fact a subset of a smaller set, and it is the smaller set of just the supported solutions. So with all of these solutions here, we are only able to find anything which is in the convex hull of the supported solutions of the regional problem. So here is a summary of the results. The supported solutions of the quadratic problem, the regional one, delivered to us weakly efficient rank 1 solutions of the relaxed problems, which are a subset of the set of all possible solutions of the relaxed problem. And the values, as long as we only take supported solutions of the regional problem, are in fact a subset of the weakly efficient solution of the values of the weakly efficient solutions of the relaxed problem, but still always supported here. You could get some results if you study just the weighted sums of the objective function. So if you fix a weight vector and study the values of this problem and the values of your relaxed problem, of your lifted problem, then in fact the values coincide, but really only for these weighted sums of the objective functions. This is just like a roundup of what we have seen so far. We stick with just points which are derived by a weighted sum, which are somehow on the convex hull in the image set. We do not get any points which are not inside the convex hull of the image set. And to illustrate this a bit further, we found a nice small numerical example which shows this to you. So here these vectors are just set to 0, so we can skip this part. We just have purely quadratic objective functions here with a diagonal matrix, and this is not much more complicated. We have a nice linear equality constraint, non-negativity, and we even did not need any binary variables, and still we already can show what we want to show to you. So this is the lifted problem, of course, straightforward, and because we're in small dimensions, we have here the cone of completely positive matrices of dimension 4, which is completely equivalent to the cone of, which is called doubly non-negative matrices. We have seen this in the beginning. It's a cone of matrices which are component-wise non-negative and positive semi-definite. We have seen this equivalence in the beginning of my talk. And now we plotted what we did have. So we have variables in R3. And in dark blue, you can see all the feasible points from the original problem. This means example quadratic problem. So from our example from the quadratic problem, from the original problem. In red, you can see the weakly efficient solutions, which is here a line. And this point here, which is now not easily seen because there's this green diamond and this green diamond here, they all are weakly efficient. The green diamonds mark those weakly efficient points which are additionally supported. Recall, any supported solution is weakly efficient. Supported solutions have been those which can be found by a weighted sum. All supported solutions are weakly efficient, but not any weakly efficient point has to be supported, which can be seen here. We have a lot of weakly efficient points which are not supported. And what is more, the weakly efficient points here on the red line, many of those are not in the convex hull of the green diamonds. They are not in the convex hull of the supported solutions. And you might recall some slides earlier, I've shown to you that we are only able to recover points which are in the convex hull of supported solutions. So the convex hull of supported solutions is what we would get. I have here a larger version in case it was hard to see on the slide before. So here the red points and here are weakly efficient. And now let's have a look on the image space. Still from the original quadratic problem, which was a non-convex problem, the values, all possible attainable values are marked here with this blue set, which is clearly a non-convex set. And the images of the weakly efficient set can be found on the lower left boundary of the set. It's here marked with red. And here this point, I zoom in. So here the red line are the images of weakly efficient points. And this point here, recall this point, for instance, is weakly efficient because you cannot find another attainable value which improves both function values at the same time. And now the green diamonds, this point and this point here, are again the images of supported solutions. So when we apply a weighted sum approach here, we minimize the linear functional in the image space. And no matter how we choose the steepness from the dark blue set, we will only be able to find this green diamond and that green diamond. Because all the other points here, the red points, are inside the convex hull of the image set of the blue set, of the dark blue set. And now we go over to the relaxed problem, to the lifted problem, the completely positive deformulation, and we study all attainable values. And now it's exactly like the convex hull of the original set with all these tail, green, whatever turquoise, I don't know what the color is named, points here. And there's here this line, which is orange or brown. This is exactly the set of image points, of efficient points of the relaxed problem. So you can see what's happening here. We make some kind of convexification. So the relaxed problem has now a convex image set, and it gets additional images of weakly efficient points, which have nothing to do with the original weakly efficient points. Images of weakly efficient points, like this black dot here, is an image of a weakly efficient point of the relaxed problem. So somehow the extreme points still have something to do with the original problem, but here we filled up a lot in the non-extreme part, and due to this convexification, we are losing all the information we require to find these red dots here. For that reason, this lifting and whatever makes no sense for multi-objective optimization. We need other ways to solve non-convex multi-objective optimization problem. And let me shortly go through this literature. So this is the paper I just presented, which has some kind of negative result. If you would like to know more about the developments in multi-objective optimization the last years, I've written recently a summary here, a survey about the last 20 years and the developments. And this is now an algorithm which allows you to solve, in fact, non-convex multi-objective optimization problems, continuous ones. It's based on a branch and bound in the Bremer space, which has the drawback that it's still not working for many variables, like many branch and bound methods in the Bremer space. If you have the non-convexity due to integer variables, but all the functions are convex, then this approach, this algorithm might be of help. We also developed something specifically for quadratic and purely integer. In the specific setting of integer and quadratic, or if you have other various types of specific structure, there exists another very well-known way of scalarizing your problem. So scalarizing is something like a weighted sum of your problem. Also, the epsilon constraint approach is a very well-known scalarization where you minimize one of the functions and put the others to constraints. Also for that, you get some nice results that you can prove that you can find all non-dominated points and how to choose your parameters. And finally, for mixed integer convex and even non-convex, we have just recently submitted a paper. So there exist developments, but I would say you cannot just use what was such a strong result by Bura. You're convexifying, which is not of a problem in the single objective setting because your solutions are still extreme ones. But as you can see here, by this convexifications, you're hiding a lot of points here of interest. And in the end, you get what you would get by a weighted sum anyway. So not of interest at all. So thank you very much for your attention. That's all what I wanted to tell. Oh, 45 minutes. Hopefully this was exactly the time I asked me to speak. I don't know.